Good morning, everyone. I was telling my class from yesterday morning that it was a remarkable spring break in that we had some of the nicest weather I've ever experienced since I've been living in Houston. So that was good. And now, of course, since it's going to be raining today and maybe the next couple of days, all of that was delayed. So that's always good when we have nice weather. So hopefully you were able to get some rest. I did what I needed to do. I got work done and things, tasks that I needed to accomplish, just like I advise you all to break things down into small pieces so that each day you get something done. Um, I've had some comments about test number two, and I'll say a little bit about that, but I need to get on to our lecture. When you turn in your test work is verification for the problems that you get correct on the Blackboard test. It's not an automatic uh, preponderance of points, okay? So if you say you do your Blackboard test and you make an 85, okay, I go through your Blackboard test and I enumerate all of the problems that you get correct, and basically, I do that by noting the ones that you have missed. And so I go through your test work and I check to see that your test work validates the answers that you have chosen. Okay. So some of you say, well, I got 0 for my test work. Well, that's actually a good grade. That means all of your test work supported the correct answers on your test. However, if the work does not support your answer, you have gaps, or you say, I guessed. I really do respect a lot of you who just say, I guessed. You lose points, of course, because there's no support. I rarely count off all the points, but I do deduct points. So just remember that your work must support the correct answers. And rarely with an incorrect answer, you get any credit. If you miss something, it's because you probably don't know how to do it, or you make a major logic error. And of course, I can't award any points for that. But I will say this, I did notice some instances of homework site solutions, because there were several papers that had the exact same solution to certain problems on the test. And I just want to comment that that should be something that you should never do. And then, of course, if you copy something and there are gaps in the logic, that's even worse. So if I teach a certain topic and a certain strategy, then I do expect you to use it. And of course, if you go to the solutions, you can look through the solution pages and see basically what I expect. I don't expect a solution that's exactly like mine, clearly, but I do expect a solution that's reasonable and that is logically deduced. So again, do avoid using the computer algebra systems and the homework sites that, again, one of my colleagues found half of my lecture notes on some homework site, which again is unethical because I certainly didn't upload them. So some of my students have taken my work and uploaded it on homework sites, which again is illegal. The thing is, ladies and gentlemen, I expect your work to have integrity. I will always expect that. I will be as fair as I can possibly be, and I will always give you a large open window for your testing. I believe in that, but I expect you to work with integrity and honesty. So thank you for your hard work, getting in your test work, and that was really nice. We had a little snafu with the Turnitin. They went down for about an hour and a half, and of course I sent you a million emails, but they had to repair it, and that does happen. Yesterday at the end of my morning lecture, my internet connection failed, and it has never done that. I mean, I've got the primo internet connection from Xfinity, and I'm like, oh, they're the best, kind of thing. But even snafus do occur. And so I'm sitting here talking, and of course the connection's bad. And when I uploaded the video to YouTube, the last 30 seconds were just gone. So again, I appreciate your patience with that. You all came through with flying colors, and I do appreciate that. The test work makes your grade legitimate. Your grade from San Jacinto College, if you are in my class, will mean something. That means the grade that you are assigned in the class will be the grade that you have earned. And that, my friends, is what pushes you to the next level. So thank you again for your hard work. Now what we want to do is move to some other types of parent graphs and then talk about inverse trig functions. So today, the first thing we want to talk about, this is going to be 5.4, will be the tangent graph. So tangent graph. Now, we have all kinds of nice tidbits about the trig functions, how we've defined them. What we found with the tangent function is that the smallest possible period is pi. So we say pi periodic. Remember, when you add a multiple of any period to the argument of tangent, it does not change the output. That's the same for all the trig functions. That's a remarkable property of periodic functions. And when you all study Fourier analysis, if some of you go on to be electrical engineers or math majors, you'll see the huge results that Fourier was able to develop with the trig functions. So this would imply that we analyze an interval of length pi. So this will be easy. If we have an interval of length pi, we'll have a complete cycle. And then, of course, the graph will just repeat for every interval of length pi to the right and to the left. So remember, tangent x, now we'll use x just because we like x for graphs. When we refer to the unit circle, we use t's for measurement along the axis or along the unit circle from 1, 0 to the terminal point like we did a couple of weeks ago. So now remember, this implies that we can consider the interval from negative pi over 2 to pi over 2. Because again, at these points, the cosine is 0, so therefore this is undefined. And these are vertical asymptotes, as we know, for the tangent function, odd multiples of pi over 2. And so this has length pi. So all we need to do is figure out what the graph looks like for this particular interval. So now, in doing this, we can look at the quadrants. So for instance, for negative pi over 2 to 0, that's in the fourth quadrant, right? We think about the clockwise where we're moving like this. And then, of course, this interval, 0 to pi over 2, is the first quadrant. And note here that the cosine is positive and the sine is negative in the fourth quadrant. And of course, in the first quadrant, they're both positive. So as we approach the 0 in the denominator, this is going to imply plus infinity. Remember, determining the sign for the vertical asymptote. And here it's negative. This will imply the negative infinity. So that tells us what the graph is going to look like as we approach each of these numbers, this one from the right and this from the left. So we basically just do our little number line. And then, of course, right in the middle is tangent of 0, which is 0. And we know tangent of 0 equals 0. That is sine of 0, 0. And of course, cosine of 0 is 1. So 0 over 1 does equal 0. So now we can get a quick graph. The tangent graph is easy. Cosine and sine are hard, but it's certainly more complicated than this one. So we want the so-called principal branch. And so now we can just type in our dotted line for x equals pi over 2. And then, of course, the dotted line for x equal negative pi over 2. And so, of course, this is where we, we're thinking we're plotting 5 million points and we don't have any calculus. But now we can see that, of course, here we get the negative infinity like we're doing a rational function. And then we move up, pick up 0, and then approach positive infinity. So we can get a nice increasing function. Go through 0. And here. So there's our tangent function, our principal branch. So it's a nice, well-behaved function away from the vertical asymptotes. Again, just like sine and cosine, it's nice and smooth, it's continuous as long as you avoid the asymptotes. And then, of course, as you keep repeating, let's just put in another branch. So, of course, here we have pi, and then we have 3 pi over 2. So again, an interval of length pi. So we can do, and we just draw the same picture. So here's another branch. There. So this goes on ad infinitum. So when I ask you to graph something, with WebAssign, they may give you several branches, but all you need to do is to determine one. And if you got one correct branch, you've determined the function. So we will always look at this piece here as being the principal branch. Principal branch. Now, the nice thing about this, it makes this function easy to invert. And so what we'll do is, again, we'll get the parents for what's left of the trig functions, and then we'll do a couple of graphing exercises that were like the ones we did in the last lecture with the transformations. Now, I know the transformations are something you know well, and you can see how simple it is to apply them to the trig functions. Now what we want to do is do the same for the cotangent, and we can do the exact same analysis. You're thinking the cotangent is just the reciprocal of this, but this is so easy to do this. We'll do the same procedure. Now when we do secant and cosecant, we'll look at it in terms of reciprocals because it's really, really simple. So let's look at these. So now we've got 3 parents. We've got cosine, sine, and tangent. Now let's do cotangent. Again, remember, cotangent is the reciprocal of the tangent. So it looks like that. So just remember, this is just 1 over tangent by definition. So we could think about reciprocating that, but let's just go ahead and use the same analysis we did for tangent because it's easy. So now notice, again, the cotangent, the smallest possible period is pi. It's pi periodic. So again, this implies analyze an interval of length pi. Just like for cosine and sine, we analyze an interval of length 2 pi, because 2 pi is the smallest possible period for cosine and sine. So now remember, here we have the vertical asymptotes. So we look for zeros of sine x. And of course, one of the principal branch would be x equals 0 and x equal pi. So we could say x equals 0, x equal pi, which would correspond to an interval of length pi right here, 0 to pi. Now, again, we can break this up into quadrants. So we have 0 to pi over 2 is quadrant 1. And just like we did before, we have cosine x here is positive, and sine x is positive. And then we have, again, now we go pi over 2 to pi, so that puts us in quadrant 2. So the arithmetic is the same. The same rules always apply. So this is quadrant 2, and this is cosine being negative, but sine still being positive. So now, again, as we approach the 0 and the pi, again, we're going to have the positive infinity. I'll just put the plus there just to emphasize it, even though it's really unnecessary. And here we have the varying sign, so we'll have the negative infinity. So now we're looking at this interval, 0 to pi. And then, of course, right in the middle is pi over 2. And that's where we get the 0. So cotangent of pi over 2 is 0. So again, like I said, this analysis is really, really simple. So we don't really have to think about reciprocating because this is easy and actually helps you with the arithmetic. So now let's do the principal branch. So we've got our x equals 0, which is what? The y-axis. So we can put in pi over 2. And then, of course, pi. We'll just dot that in. Don't worry about dotting the x-axis or the y-axis. I mean, we don't usually do that, so that's no problem. So x equals 0. So now, of course, we have the 0 at pi over 2, but now notice as we approach the 0 here, we get the positive infinity. So we're up here, and then we come down. So I'll do something like this. And then as we approach pi, we proceed to negative infinity. So the branch looks similar to that of the tangent function. So you're thinking, based upon our very intuitive picture, it appears, at least in terms of what we've drawn, that the tangent function increases on its principal branch, where the cotangent function is falling or decreasing. Now, of course, we know that's not a proof, but when you get to calculus, you'll be able to prove this. But for now, this is more than sufficient. And to be honest with you, you'll take all of this with you to calculus, and once you prove it, you'll be like, yeah, I already knew that. But again, we can look at this and say, just like the tangent function, we can just replicate this to the right and to the left. So when you are graphing a periodic function, and we haven't had a lot of practice with periodic functions, you really have less work. You basically have to look at an interval of length pi. Now, why do we choose this particular interval of length pi? Because it's between two asymptotes. And so it gives us a neater picture. We don't want a picture that's broken up. So I just basically list the principal branch, and we can just replicate this, like I say, on either side ad infinitum. So we'll think of this, ladies and gentlemen, as the principal branch. Principal branch. Now, when you think about this curve and the tangent curve, you're thinking, not so bad. So when we think about transforming a cotangent or tangent curve, we're going to look at what happens to these asymptotes and this point. Now, if we need an extra point, just for verification, we can take a simple point like pi over 4, and of course tangent of pi over 4 and cotangent of pi over 4 is 1. So if we've got a reflection in the x-axis, just to make sure our graph is right, we can always check a point that's not on the x-axis. So basically, as we do these functions, we have fewer objects to move than we did for the sine and the cosine, but still the basic approach. So now here's something that's important. With the asymptotes, the vertical transformations don't affect the vertical asymptotes, but clearly the horizontal ones will affect the vertical asymptotes, shifting and compression and stretching. So we need to be sure that we change the asymptotes when it's appropriate, but leave them alone when the transformation doesn't impact them, just like we've done before. So there's our second parent. So that gives us 4 parent functions. Now let's look at the secant function and think of it as a reciprocal, because it's really simple to actually sketch the secant function if we just look at the cosine function, basically because the cosine function doesn't have any asymptotes, and it's easy to figure out the asymptotes when you've got a nice continuous clean function. So this will be secant. Remember the terminology: sine, cosine, cofunctions; secant, cosecant, cofunctions; tangent, cotangent, cofunctions. Keep thinking that, because that's going to have an impact soon, later, but soon. Okay, so now just remember that secant is the reciprocal, the mathematical reciprocal of the cosine. We just invert it. So here's a real easy way. And of course, we just consider an interval of length 2 pi. Now, what I'm going to do, ladies and gentlemen, is I'm going to make sure that I get all of the asymptotes in the interval length of 2 pi, so that we've got a nice clean graph. So here's what we're going to do. We're going to draw part of the cosine function that will be of length 2 pi. So we'll start at negative pi over 2, then we'll have 0, pi over 2, then we'll have pi, and then 3 pi over 2. So of course, this is a length, interval of length 2 pi. Now let's go ahead and put in our 1 and minus 1. Again, this is very intuitive and actually kind of fun. If you think about how I'm doing this, you won't forget these techniques. So let's dot in this case, the cosine function. So let me get some points here. Of course, we don't put in the points, then the graph looks pretty bad. So here's our reasonable cosine function, okay? So now, like I said before, this is a reciprocal. So now notice as we approach pi over 2, here we're getting infinity. That is, we're approaching division by 0. That defines an asymptote. So now we can say when we reciprocate, that 0 will develop or produce a vertical asymptote at pi over 2, negative pi over 2. And we know it's going to ascend to positive infinity because the graph to the right of negative pi over 2 is positive. Now, of course, here the 0 will also produce a vertical asymptote as we reciprocate. If you reciprocate 0, which you really can't do, it gives you undefined, right? So we get x equal pi over 2. And then, of course, 3 pi over 2 will do the same thing. And then, of course, if we just keep repeating this same interval of length 2 pi, we'll get the same graph. So all we need is the so-called principal branch. And we're going to have 2 branches here in the principal branch because this is discontinuous. So now, of course, this is what makes this easy. If we reciprocate 1, we just get 1. But then the graph will ascend to positive infinity here. And then the graph still ascends to positive infinity here, like that. And then, of course, we do the same thing here. Reciprocating negative 1 is just negative 1, but then we descend to negative infinity and do the same here. So the reciprocation process using the cosine function is very easy to get the basic parent function of the secant. So now we're thinking, oh, okay, this is more like the cosine function in terms of what we have to figure out. So when we transform a secant graph then we've got these, what, three asymptotes, which kind of enclose the principal branches here, x equal negative pi over 2, x equal pi over 2, and x equal 3 pi over 2. And then we've got these two intermediate type points. We have 0, 1, and pi negative 1. So when we transform a secant function, we would want to know what happens to these objects, just like a sine and a cosine. And so we would move the asymptotes if necessary and move the points if necessary. And then we plot the new objects and draw the new function. So again, we want to focus on the actual principal part of the curve and then fully develop that. And once we have that, then we know that the curve just repeats to the right and to the left. So again, the periodic function does give you less work than a standard non-periodic function. But you know, new is new, and so that is more difficult at this point. Now, for the cosecant, we'll do the same procedure. So again, these are functions that if you have note cards or you look at formula sheets, these make great little little drawings for note cards just to give you that reminder of what the principal parent graph looks like. Again, you'll commit these to memory. But when you're working quickly and things, it's always nice to either use a formula sheet that you have on Blackboard or just put these on note cards just for easy reference. Usually very good. And I think the formula card from this book is really good. So you can use that if you like. Now, let's look at the cosecant, and we'll do the same procedure. So here we have cosecant. So remember cosecant, this one's kind of odd. We do CSC, cosecant, and this is 1 over sine x. Again, consider an interval of length 2 pi. We're just trying to cut down on the amount of work. And in math, we have to do that. We always have to do that in math. There's always plenty of stuff to figure out, just like the test question about building the box. Remember, I did that in lecture. I put the same kind of problem on the test. Very few of you actually analyzed it as I did in class, but still, you think, my goodness, you got to put the formula together, then you got to factor it, with the rational zeros, and then figure out which values of x make any sense. So even the straightforward problems take steps, several steps. So we want to make it as efficient as we can. So now let's again, what interval are we going to use here? Well, let's take an interval that will include zeros at the endpoints, just like we did for the cosine function. So we'll do 0 to 2 pi this time. So we'll do 0, pi over 2, pi, 3 pi over 2, 2 pi. So I'll extend this a little. And then we'll do a 1 and a negative 1. So we'll go ahead and plot our points for our sine function. Again, the unit circle is where it all begins and it will all end there. So the unit circle is our beginning for trigonometry. It gives us everything that we're developing. So let's dot in a reasonable sine function. And we'll use the same technique. You have to admit that the geometry of the unit circle does make our interpretation of geometry very doable and very arithmetic as well as algebraic. So now we're thinking all of these zeros here of the sine function will define vertical asymptotes because the cosecant is the reciprocal of the sine function. So of course we have x equals 0, and then we'll have x equals pi. And then of course, we'll have x equals 2 pi. Very simple. There's no guesswork here. The only guessing you do is that what you do when you don't know what you're talking about. Don't guess. There's never a reason to guess. I love when you all send me messages. Why is this way? And I'll say, that's a good question. It's just a definition. Sometimes it's as simple as just being a definition, and that's it. So now notice we reciprocate 1, but that just stays there. And then of course here we ascend to infinity on both sides, just like we did with the secant. Again, this is not Rembrandt, clearly, but that's good. We're not worried about it being picture perfect, just reasonable. And now, of course, if we reciprocate -1, we get -1, and then we descend to infinity here. So here's our so-called principal branches, sandwiched between two vertical asymptotes. So you're thinking, this function's not as well behaved. It has vertical asymptotes and it's clearly discontinuous, just like tangent and cotangent. So now again, just like before, this is why it's kind of neat to think about how we constructed these principal branches. We think about the objects that we have. We have x equals 0, x equals pi, x equals 2 pi. So we would need to move those around for the transformations. And then of course, these 2 points here. So every time we, again, look at a cosecant graph, we would want to move these objects, just like we move points in cosine and sine. So we can then draw fairly easily the transform function, okay? So again, you might find this to be easier than the sine and the cosine, basically because it seems to be a little bit less work. Now let's just do a couple of examples, and then we're going to use these functions to create inverse functions by chopping them up and making them one-to-one. So that'll be fun. And of course, we need these parent functions to do that. So I've got a couple of examples here. They're easy. Let's see. Yeah, let's do a tangent and I think I've got a tangent and a secant. So here's an example. So what we want to do is graph. So we'll say graph a complete period. Now, so of course, when we look at a function, the period could change, right? So we just want a complete period. And if you want to add extras, you can. We could always tack on some, but one complete period is all we need. And so here we have y equals the tangent of 2x minus 2 pi over 3. So of course, you're thinking with these new functions, doesn't really make a whole lot of sense to multiply them by numbers like, we think of a vertical stretching. I mean, at least for secant and cosecant, that will move points, those intermediary points, that'll move those. But for the tangent and cotangent, it's like, well, what's 3 times infinity? Well, that's just infinity. So you might find that that's a little bit, not needed, but we certainly want to be careful when we have negatives multiplying a function, because that's an x-axis reflection and that flips everything. So that is indeed important. Now, of course, we want to approach this like we did the cosine and sine. So first we want to make this monic. So we factor the 2, just like we always do. So we have x minus pi over 3. So basically here we've got 2 transformations going on. We've got a horizontal compression and then we have a right shift. So just like the sine and cosine, we use the same techniques to factor this so we can reveal the actual horizontal transformations. So now let's write it down from the parent. The parent function is clearly tangent. So we'll do h compression by 2. So this will be tangent of 2x. And then for the second, we want to do a right shift by pi over 3. And then, of course, we'll change denominators if we need to for the arithmetic to be easier. Right shift by pi over 3. It's always good to make sure you have common denominators so the arithmetic is really easy. So we get tangent of 2 times x minus pi over 3. So that's the complete transformation. So now let's think about our principal branch. We have x equals negative pi over 2. We have x equals pi over 2. And then we have the nice point, 0, 0, right? Tangent of 0 is 0. So we're thinking we don't have an x-axis reflection. So these objects will be sufficient to draw the new function. So now notice here, we do an h compression by 2. So all the x's get divided by 2. So this will be x equals negative pi over 4. Oh, well, let me not write it above the arrow. Let me move it over. Let me write it here so it's, yeah, where it needs to be. Pi over 4. Again, h compression by 2. X equals pi over 4. Divide by 2. And then, of course, the 0 is not impacted. Now notice for the last one, we need to do a right shift. And again, I'm gonna erase this and make a note here. We've got a right shift by pi over 3, but we don't have a common denominator. So that's a little bit untoward. So let's go ahead and clean it up. For the 3 and the 4, we need a 12. So we can say this equals, we'll just say 12. So negative 3 pi over 4. Just clean it up so we have a nice arithmetic going on. And then, of course, this will just be a 12 and a 3 pi. And then, of course, here we still have 0, 0. And now, if you like, we can go ahead and think of this again with a 12. And this will be what? 4 pi. Right there. So now when we add the pi over 3, we're adding 4 pi over 12, and that makes the arithmetic a lot easier. So here when we add, we get what? A 4 plus a negative 3. So this x equals pi over 12. And here we get a 4 plus a 3, so that's a 7. X equals 7 pi over 12. And then, of course, here we're just adding 4 pi over 12 to 0. So that gives us 4 pi over 12, comma 0. Now, the nice thing about this is that all of these points here, all of these objects have the same denominator, so we can spread them out and with tick marks of pi over 12. And that way the graph is nice and structured. The idea here is that because we have the pi's, we can make the actual object graphs very consistent with the parent graph. And so when you draw this and when you're checking for a correct graph or you're checking WebAssign, you've got these points as a way to validate your graph. So now we can use these new objects to graph the new function. So let's do it. And all we need is one complete period, so that's all we'll draw. So notice here, and this is very interesting. Notice now, as we look at this, we go from pi over 12 to 7 pi over 12. That's 6 pi over 12, which is pi over 2. So we know that we have compressed the period by a factor of 2. We expect that. So these numbers are consistent with that transformation. So we'll do a 1, 2, 3, 4, 5, 6. So we'll just go ahead and say pi 12. And then we have 2 pi 12, 3 pi 12, 4 pi 12, 5 pi 12. So 1, 2, 3, 4, 5, 6 pi 12, and then 7 pi 12. You don't have to do all of these. You could just plot these, but I just wanted to show you now that we have a nice uh, uh, interval uh, display with equal subintervals, which makes for a much cleaner graph. So now pi over 12, we'll go ahead and dot in the vertical asymptote. This just gives the graph disposition. It gives it placement on the XY plane, gives us placement. So we're not just drawing it and like, you know, being haphazard. We're haphazard enough because we're just doing a reasonable facsimile. And so now for 7 pi over 12, we can do the same thing. So we have x equals 7 pi over 12. And now we've got our nice point, 4 pi over 12, 0. We'll do this in red. We've got that right there. And so now we know what the parent looks like. So we just draw it in.
Professor.
Did someone say something?
Yes, it's me, Simon.
Yes, what's your question?
Yarlene asked a question. I was kind of thinking the same thing. Up there where you have x equals pi over 4, you said it equals pi or 3 pi over 12. How did you get 3 pi over 12?
Oh, right here?
Yes, sir.
Oh, okay. Okay, 4 into 12 goes how many times? 3, and 3 times negative pi is negative 3 pi.
So you just multiplied it by 3?
Right, right. Just a common denominator. Let's look at it this way. Say you've got a denominator of 4 and a denominator of 3. What's the least common denominator? Would be 12, right? So the LCD equals 12. That is, when we're trying to add fractions, we need to have a least common denominator, and that's why I use 12. Is that clear?
Yes, thank you.
Okay. Again, Simon makes a good point. This is just, think back to least common denominator when you do rational equations and you're trying to clear denominators, right? And say you had these two denominators in your equation. How could you clear it? Well, you have to do the LCD. Why is the LCD 12? Because they're relatively prime, okay? Now, notice again, we have all of these vertical asymptotes that look like this, and then we have a shift that looks like this. Now, if I've got to, in this case, add pi over 3 to negative pi over 4, I need a common denominator, right? So I choose the common denominator of 12, and it's also the least, okay? So that's an excellent question, Yarlene and Simon, so good. And so I'm sure everybody else in the class is breathing a sigh of relief. But see how nice this is? See, when we get these nice points with the common denominators, we can spread out our work, and it's very clear where these points are and these objects are. Okay, and here's our complete graph. And then, of course, if we want to do this again, we just add 6 pi over 12 to 7 pi over 12, and that'll give us 13 pi over 12, which will give us another principal branch. So once you do this, ladies and gentlemen, you're done. You don't have to worry about doing 500 of these. You have one, and that's clear, and that's all that you need. Remember, a periodic function repeats. Now, you kind of have to get used to this new object, the periodic function. Like I said before, the only time we've ever seen a periodic function is when we just drew it, okay? But we didn't draw the equations. Now we have functions defined by the unit circle, which are actually periodic based upon what? The circumference of the unit circle. So again, just remember here, this is just a technique to make the arithmetic easier so that we can have a much cleaner graph, okay? Now, let's do another one that's similar to that. But again, like I say, If you don't do this, then you're going to be hard pressed to come up with good numbers here. I don't want a bunch of decimals. I look at that and cringe, of course. You know, we want exact work here. Just like if you were just adding these two numbers, you know, with a common denominator, you get what? 7/12, right? So it's the same thing you've always been doing. Just don't let the pies scare you, okay? Now, let's do another one. The next one I want to do is so we can get practice with the cosecant and the secant. So we'll do a secant graph. So we have 3 secant. This is what I was talking about before. Pi times x plus 1/2. Well, the author was really good to us here. We want to graph a complete period. Now, when you look at this, you're thinking, well, the last problem didn't have this luxury. This is already factored. And so if you like, you can say, well, the argument is just all of that. So now it looks like we have an H compression, we have a left shift, and then we have a stretch. But this stretch is actually something we'll be able to see because we have those intermediary points on the secant function that like, okay, well, we'll move them up. You know, when you multiply 1 by 3, it does move the point up. So it's not completely useless. So let's go ahead and map out the transformation. This is the same thing we've been doing from day one. So none of this is new. The only thing that's new, ladies and gentlemen, is like when we did the logs and the exponents, we have new parent functions. So you need to commit to memory because you understand them, these new parent functions, okay? So now we want to do an H compression by pi. Of course, pi is bigger than 1, H compression by pi. So we get secant pi x. And now, of course, we want to replace x with x plus 1/2. So that's going to be a left shift because of the plus by 1/2. So left shift by 1/2. So we get secant pi x plus 1/2. You can put the bracket there if you like. And then the very last one is a v stretch. We'll multiply the entire function by 3. So we'll say v stretch by 3. When you get to calculus, you'll be talking about determinate and indeterminate forms, and you will learn more about how infinity works. When you have, you know, infinity times infinity, that's still infinity. But when you have infinity minus infinity, that's not determined to be 0. It's indeterminate because infinity is not a number. So when you get to calculus, you're going to work on some neat techniques. We've already actually talked about it in this class, but not in the way that you will in calculus. So there'll be opportunities to deal more with infinity as you get to calculus 1 and calculus 2. So now what we want to do is say, okay, we've got these 3 transformations. Let's consider the objects. So we've got the x equals negative pi over 2. We have x equals pi over 2, and we have x equals 3 pi over 2. So let me get our friend secant. So this is what I'm referring to. These asymptotes here, we need to move, and then we need to move these 2 points. So we're going to get what? 0, 1, and then pi negative 1. Again, 0, 1, pi negative 1. So the 1, 2, 3, 4, 5 objects that we want to move so we can figure out what the new graph looks like. So these are the objects here. So we do H compression by pi. So we're going to divide all of the x terms by pi. So that's nice. The pi's here will absorb. So when you divide by pi, we get x equals negative 1/2. Again, the pi absorbs. And then we get x equals 1/2. How nice, same denominator, right? And then of course here the pi absorbs and we get x equals 3/2. Now notice here, when we divide 0 by 3, that doesn't change, or by pi, no change. But here, when we divide pi by pi, we get 1. Okay, so remember, all of these have x's in them. So when we do a horizontal compression, all the x's are changed, okay, just like we did before. So again, remember, these are the 5 objects that we want to move when we're dealing with a secant function. Now notice we have a left shift by 1/2, but these denominators are all consistent with that. So we don't have to change the denominator like we did the last time. So left shift means we subtract. So subtract 1/2, that'll be x equals -1. Subtract 1/2, x equals 0. Subtract 1/2, x equals 1. Subtract 1/2, -1/2, 1. Subtract 1/2, 1/2, -1. So again, compare this to the last problem we did. We did not have to change the denominator because they're in agreement, okay? So less work. Now the very last one here, we have the left shift, which we just accomplished, and then we have the B stretch. So this means in this particular case that all the y coordinates will get multiplied by 3. Notice the first 3 do not change. They're only vertical asymptotes, x's, so no change. X equals -1, x equals 0, x equals 1. But then of course the 1 and the -1 are the y's. They get multiplied by 3. So -1/2, 3, 1/2, -3. So again, these new objects define the transform graph. So, you know, ladies and gentlemen, by this time, the transformations will, I think, have sunk in. I remember a colleague that my first semester teaching at the South Campus when I graduated from A&M, this person is now working in Austin. I told him, I said, go to Austin and make those 6 figures. I think he's going to be in product development. But we both agreed that the neatest thing about trigonometry was that we would get to use the transformation processes that were developed in college algebra and how it made the transition to trig graphs so much easier. Again, you just want to make sure that whatever you graph, you have some confidence in. And these techniques you will take with you to engineering. You'll take with you to physics. You'll take with you to future mathematics courses, because as long as they're reasonable graphs, this technique is very, very accurate and you know, reasonable to do. You certainly wouldn't want to apply calculus to this. That would be a waste of time. You will figure that out when you get to calculus. Now, let's go ahead and graph these points and these asymptotes, and we'll have our principal branch, our complete period. So now you can spread this out as much as you like. Notice we've got the -1, the 0, the 1, the -1/2, and the 1/2. So let's spread it out. So we've got -1, we've got a -1/2, we have the 0, we have the 1/2. Well, I'm saying spread out, but you know, spread out enough. And then we've got the 1. So let's draw in the vertical asymptotes. So we have x equals -1. And then of course we have x equals 0, just the y-axis. And then we have x equals 1. Again, my spacing is a little bit awkward, but tried to space it more as I got to this side. So not Rembrandt, clearly. And now, if you like, we can say 1, 2, 3. Do any kind of scale you like. Doesn't really matter. So here's our -3. And here's our 3. So we've got -1/2, 3 right here. and then we have 1/2 -3. And now we can just simply draw the branches using our parent function. So this is really easy. This is easier than graphing a quadratic. Quadratic functions are complicated. I mean, we've got like tons of algebra to do with quadratic functions. These are really simple. And so again, you've got this piece that you can replicate. So the next one would go, this goes from -1 to 1. The next one would go from 1 to 3, and then 3 to 5, etc. And then on this side, -3 to -1, and you just replicate this over and over. So what's nice about this is when you're doing your WebAssign or you're doing your homework, you can look at your principal branch and you can check the points and the asymptotes, and you can clearly choose the graph which is correct just based on this analysis. And now, of course, the thing is, depending on the complexity of the transformation, you may do less work or more work. Of course, when you've got these horizontal transformations, they usually take a little bit more work. But if you've just got a reflection in the x-axis or upward V shift, those are simple to do. You don't even have to do this. You can just kind of see it in your mind's eye. So what I wanted to focus on are the horizontal transformations, which will usually give you the most difficulty. And again, these students will always send me messages and say, where did these points come from? I said, well, just remember that if you move the basic objects via the transformations, you get the points and you get the new asymptotes. So that will be a way to clear up all of the fog, so to speak, as you work through these. The nice thing about a computer generated plot is that it just plots a lot of numbers, and you can program your algebra system to plot certain objects. Okay, and so you get a nice, pretty picture. But you know, you have to do that work. You have to do that work to show me that you understand this. And then, of course, later on, when you take a engineering class, you may write your own program to do some type of modeling task. Many of you will take some computer science to get some basic coding down that you will use in engineering. And in some engineering classes, they'll teach you some coding. So computer science will, of course, impact all of you all, regardless of what field you plan to study or pursue. Now, what we want to talk about is, again, graphs are not so bad, and you're thinking maybe not the focus, because we're really all about solving equations when it comes to algebra. And so the ultimate thing that we'll do with the trig after we get through all the identities will be to solve equations. So you'll feel like you're in an algebra class again. But in order to do that, we need to talk about inverse trig functions. So this is a very important topic, and you'll think at this point we're just learning new parent functions, and it's true. That's what we're going to have to do. Inverse trig functions. Now, I always talk to my students and let them know there is a great, really, really nice Wikipedia page on inverse trig functions. Everybody gives Wikipedia such a hard time, but it's a storehouse of all kinds of knowledge. It's free. It's public domain. It's available to you, and there's lots of valuable information there. And so a lot of times I'll tell students, if you're trying to compile some formulas, I mean, you got your formula sheets on Blackboard and you're just looking for a different perspective, or maybe you read the book, it doesn't matter. It's a very nice layout of a lot of good mathematics. So when we think about inverse trig functions, we need one-to-one functions. We need one-to-one functions. And as we can tell right now, none of the functions that we're working with, the 6 trig functions, are one-to-one. We know that they're even or odd. We do know that, but when we draw these periodic functions, they repeat. And so we don't get the one-to-one. So what are we going to do? Well, let's start with the sine function. And what we're going to do in this case is we're going to restrict the domain. So we need one-to-one, so we restrict the domain. So when we think about that, we're going to use, there'll be two notations that you'll see in the literature. One will be the superscript -1, and the other will be arc sign. So for instance, we'll say y, for now, we'll just say y equals the inverse sine of x. So we're going to say inverse sine of x for the inverse function. Now, of course, there's another notation called arc sign. I'll just write this below. You'll also see it written this way. In Wikipedia, they like to use arc sign. I don't mind either, but I kind of like the not -1 just because it kind of focuses on the -1 notation from college algebra that we use often. But again, I'll focus on this in this class, but if you see this, these are equivalent. Now, the idea is that if we define y to be the inverse sine, we can apply sine to both sides. So x will equal sine of y. And when is this going to be true? That is, if we apply sine to y, we get sine y. And if we apply sine to inverse sine, those two functions are inverses and they basically absorb each other and we're just left with x. So if we say this, we're automatically saying this. We have to, just like doing the logarithm definition. Now, when is this going to make sense? Here's the new domain. The domain of the inverse trig function, here the inverse sine, will be -1 to 1. And the range will be -pi/2 to pi/2. So you're thinking, oh, I see what you're doing, Professor Ron. You're reading the unit circle backwards. So what's that going to mean? Okay, well, let's draw it. The inverse sine function is 1 to 1 because we restricted the domain of the sine function. So we get -1 to 1. We get our pi/2 and our -pi/2. And so we're taking that branch that we restricted from the sine function and we reflect it in the line y equal x, and we get a graph that looks like this. There we go. So this is y equals inverse sine of x. And what's nice about this function is we've got vertical tangents here at the endpoints, but it's a nice increasing function. So that's inverse sine. And again, it's 1 to 1 as it should be because we restricted the domain here from the sine function. So with sine, we restrict to this domain and we get this output. And of course, the domains and the ranges for the functions flip. And this gives us, again, this gives us a nice 1 to 1 invertible function. So we can go from inverse sine to sine. Now, this graph we need to know. If you know this graph, you know this, which is important. Now, let's write down the inverse equations, just like we do for sine, for log and exponents. So we're going to say sine of inverse sine of x, just like we did over here, that's going to be x. But if and only if, in this case, x lives between -1 and 1. Again, when you say this, we say, well, what does this need to be? Well, we need to have the range of the sine function, and we know the sine lives between -1 and 1. So if this is actually going to have an output of x because the inverse sine and sine absorb each other, then this needs to make sense, and that's valid. So of course, this we can always write as long as this is true. And then 2, we can flip it around. Let's do the inverse sine on the outside. And now what we need to see is that the output should be in the range of the inverse sine function, which will be here. So this will be if and only if x lives between negative pi over 2 and pi over 2. So the key here is that you're thinking, well, so what? Well, here's the beauty of all of this. When we actually restrict the domains and define these functions, we create functions that give us reverse paths and also give us some really nice calculus. And so that's why inverse functions are so important, and we want to be able to write them down. So now one thing that's very nice is that the inverse sine function is actually odd. How does it deal with the negative argument? It factors. So that's nice. That's just like the sine function. So it's an odd function. So we can say odd function. Of course, it's got a nice symmetric domain about 0. Don't have anything to worry about. And so like, very good. Now, not all the functions are going to behave this nicely, ladies and gentlemen, but we love the inverse sine function, and it'll be something you'll spend a lot of time on in calculus. We're going to talk about the inverse cosine, but it doesn't get as much play as the inverse sine because the derivatives in calculus just differ by a negative sign. But again, as you do your parent functions for the basic 6 trig functions, you need to do your parent functions here for the inverse trig functions. So all of this should go on a note card and something that you can sketch out and draw. Again, we make the sine function one-to-one by restricting the domain. That's how we create the, it's like taking a quadratic function and only taking one branch of the parabola to make a what? A one-to-one function. So this is a similar technique that we've seen before. Okay, so let's do inverse cosine. Inverse cosine will be done the same way. So we're going to say inverse cosine. We know the cosine function is not one-to-one. And I will say these definitions are universal. The inverse secant is kind of a thorn in our side, but that's just the way life is. I think sometimes the mathematicians should get together and just decide, okay, you know, we're gonna define this function to be this and stop all the confusion. But you know, there always have to be kinks in things. So now when we look at this, let's just say the following. We're going to say y equals the inverse cosine of x if and only if x equals cosine y. So we're going to define this the same way we did before. We're going to start with the inverse cosine and then apply cosine to both sides. So if we say this, we automatically have to say this. And ladies and gentlemen, of course, there's an alternate notation, arc cosine. I don't want you to be disturbed when you see this and think, well, what is that function? It means the same as this. And some calculus text will use this, some will use this, and some do both. So be aware that you will see this if you go to the Wikipedia page. Now, what does this mean? This will be if and only if. Again, the domain of the inverse trig function is going to be the same as it was for inverse sine, negative 1-to-1. Again, the range of the cosine now becomes the domain. And then the range is going to look a little bit different. It's going to go from 0 to pi. And then you're thinking, oh, that's going to wreck even or odd. That's so much for that. You know, I mean, well, it's not going to wreck it, but it does cause an issue. So the thing is that now the function is going to look a little bit different. So again, when we think about this definition, again, this is a universal definition. So every time you see inverse cosine, it will be defined this way. So let's draw the picture. So again, the domain runs from negative 1 to 1, but now the range is 0, pi over 2, and pi. And so now we just flip everything around. We'll get negative 1 pi 0 pi over 2, and then 1, 0, just flipping the coordinates on the unit circle. So let's draw this. So now you're thinking that looks somewhat like the inverse sine function, but now it's decreasing. So this is y equals inverse cosine. Now, the nice thing about this is that if you know this graph, you know this. You've got the range and the domain. So again, we say that cosine of 0 equals 1. So inverse cosine of 1 equals 0. We just take the unit circle and work it backwards. So there's nothing new about this. It's just interchanging the x's and the y's when we think about the unit circle. Like we'll go from t to the terminal point. Now we're going from the terminal point to the t value. So just the reverse path, so to speak. Now, what do the inverse rules look like? So we'll do cosine of inverse cosine of x. That should be x because, again, the inverse function and the cosine, they absorb each other. But when is this going to work? This means that the range here needs to correspond to that of the cosine function. So if and only if x, in this particular case, is where? Think about that. In this particular case, this would be what? Negative 1, 2, 1. Now, one thing that we want to think about that's really important is just like with the sine function, inverse sine. Let's go back and compare. See, we want to make sure that whatever output we have is in the range. So this will be the same. So these will correspond. And now too, we do inverse cosine of cosine of x. We want that to be x, but we want the output to be in the range of the inverse cosine. So this will say if and only if x lives between 0 and pi. So this has the same nature as the inverse sine function, but we have one little hiccup here. We don't have the nice function. You can look at this and say, well, this is not going to give you symmetry with respect to the origin like we had for the inverse sine function, at least the way we drew it. So now we actually have inverse cosine of the negative argument will be pi minus the inverse cosine of x. So again, this is not an odd function. So this is one little hiccup, but this is an important identity. Again, the idea here is that if you want to think about this in terms of function transformations, this is a way to actually validate this. But again, we don't have the luxury of having an odd function with the inverse cosine. The only ones that are going to turn out to be odd are the inverse sine and the inverse tangent. So this is just one little hiccup that we'll have to worry about, but it's an important hiccup because this will come in very handy when you're doing calculations with the inverse sine functions or the inverse trig functions. What I found, and that's why I like the Wikipedia page, because again, books try to give you as much as possible, but as a math professor, I know what you're going to need to be able to do when you get to the calculus sequence. So I add this in as an extra identity so that you can actually use it and be familiar with it when you get to calculus and ride the wave, so to speak. So again, remember, parent function for the inverse cosine. If you know this, you know this. This is the basic definition, just like we did with logarithms. And then these are the inverse equations that, again, we are obeying the range and domain. Again, we must obey this because we've restricted things. We can't just go out, at random. We have restricted the domain of the trig function, so we have to respect that. Okay, now let's look at the inverse tangent. Inverse tangent is the easiest one, and it's one of our favorite functions. Inverse tangent. So in this particular case, we're going to say y equals inverse tangent of x if and only if x is equal to tangent y. Now, of course, you'll also see this y equal arc tan. That is another symbolism for the inverse tangent, which you will see. Again, you just put arc in front of the trig function. Not sure so much about the history of this. I know this probably came first and this came later because this was notation that mathematicians liked because it was simple, but this still has survived. Now, again, you're thinking the principal branch of the tangent function is already one-to-one. So we don't have to work as hard like we did with sine and cosine. We can just go ahead and take that principal branch. So we'll say the domain, in this case, will just be what? All real numbers. Because we know that the principal branch runs from negative infinity to infinity. And then, of course, the range will be the domain, which is the x values between the two vertical asymptotes. And that'll just be negative pi over 2 to pi over 2. So you think of that principal branch and you flip the range in the domain and you get exactly this, just like we've been doing. So now we see this is a little bit easier, maybe more user-friendly. And then, of course, now we can say, what does the picture look like? Well, we just, again, reflect in the line y equal x. So the vertical asymptotes become horizontal. So we have y equals pi over 2. And we have y equals negative pi over 2. And then, of course, 0, 0 doesn't go anywhere. And so we get what looks like a cubic function. Right there. So this is y equals inverse tangent. Students love the inverse tangent. It's the easiest inverse trig function because it's so user-friendly. So they can remember the principal branch, and then it's like, I got this one, Professor Ryan, you can move on. So here's one breath of fresh air when it comes to the inverse trig functions. The inverse tangent is your friend. It's the easiest one to remember. Now, let's write down the inverse equations. So we'll say tangent of the inverse tangent of x will be x. Again, we want this to be in the range of the tangent function. So we'll say if and only if x lives between what? Negative infinity and infinity. That's easy enough. And then 2, we'll say inverse tangent of x is x. Again, we want this to be in the range of the inverse tangent function, so it must live there. Well, let me do a little element sign. Okay, so again, what students find, at least when they meet the inverse trig functions for the first time, they focus on the actual picture, and then the picture gives you this. So just like we think of the parent functions for the basic 6 trig functions, we can do the inverse trig functions the same way. And again, familiarity means that you sit down with a clean sheet of paper and just start drawing them and start writing them down. Now, another nice attribute, why do we love the inverse tangent? It is an odd function. And you can see our graph looks like that. Of course, that's not a proof, but it is an odd function. And as we have time, we'll go back and we'll do some of these proofs. Right now, I just want to give you all of the details because this is a lot to take in the first time you see it. I want you to be able to work with this and take it in and become familiar with it. So we see this is an odd function, just like the regular tangent function. Again, our picture looks like it has symmetry with respect to the origin. Of course, that's not a proof, but we get the nice characteristic of the inverse tangent function being odd, just like the inverse sine. So we can always factor the negatives. We can always deal with the negatives. Okay, so inverse tangent, turns up a lot. The calculus is very elegant, turns up a lot in calculus sequence. Of course, you use this to make a probability distribution function, so it turns up a lot in probability theory. A very, very useful function. So again, they're defined and they stick around because they turn out to be really useful. Okay, now another function that we deal with is the inverse secant. Now, this is kind of a bugaboo, and I say that, and of course that dates me quite a bit. Bugaboo, that just means it's like a thorn. I like the phrase thorn in your side. There is no universal definition, ladies and gentlemen, for the inverse secant, but one I'm going to use is not the one that's in the book, but it's the one that we use in calculus. And so don't worry about it. Just focus on the one that I give you in class, when you're studying. So we're going to say y equals the inverse secant of x if and only if x equals secant of y. Now, the alternate notation is arc secant. Again, arc, just throw arc in front of the secant, in front of the trig function, and this is another way of displaying this object. We will focus on this. I like it, but this is also used. And I will just say that to remind you. Now, again, the domain is going to be a little bit different in this case. It will be that, like, we know we go from 1 to infinity and negative infinity to negative 1. So that becomes the domain of the inverse trig function. So we have negative infinity to negative 1, union 1 to infinity. And then, of course, now this is where the change comes. The range will live between 0 and pi, but of course, we don't get the pi over 2 because that's a vertical asymptote in the secant function. So we get pi over 2, open, union, pi over 2 to pi, closed. So this is where the actual definition changes. Some other books are different from this. It's shifted, and that's fine. But in terms of calculus, I like this function, and it's the one I teach when I teach calculus. So we're going to use this one. Now, again, inverse equations, secant of inverse secant. Again, this needs to be in the domain of the secant function. So when you look at this and you say, okay, in the range of the secant function, so you look at this and say, well, we flip these around and we know x has to live here. If and only if x is an element of negative infinity to negative 1, union 1 to infinity. And then 2, inverse secant of x. Again, these will absorb, but again, this needs to be in the range of the inverse secant, which puts it over here. So once you write this down, these are easy to do. So this is all, again, some of you may say, well, why is it this way? This is how these are defined. This is what we do to restrict the domain of the trig functions to make them one-to-one, and therefore we can define an inverse function. We can define an inverse path. And so now what's nice about this is that this gives us a really interesting picture. And one of my favorites in calculus. That is, we've got this horizontal asymptote that was a vertical asymptote in the secant function, right? The 0 of cosine, so we have y equals pi over 2. And then we have the 1 and we have the negative 1. And then, of course, up here we have pi. So we start at 1 and then we approach. It's like reflecting that principal branch in the line y equal x. So now we approach the horizontal asymptote, y equal pi over 2. And then here we do the same, but we ascend to this point, negative 1 pi. Now, one thing that's nice about this definition is that this definition actually produces an increasing function. And some mathematicians prefer that. I'm one of them. And also with this, we get a nice reciprocal rule. And I'll say this, it's not, I'll just write this reciprocal rule. I usually like to state this. That's why this is actually nice. If you don't have an inverse secant button and you're trying to approximate a value, you can use this. Inverse secant of x can be computed as the inverse cosine of 1 over x. This is the reciprocal rule. And we get this because of our definition. That is, what you're seeing here is that the ranges of the inverse cosine and inverse secant are compatible. This is contained in the range of the inverse cosine. So we get this nice reciprocal rule here. And also, it's clearly not a odd function, but we have, how does it react to negative arguments? It's the same as the inverse cosine, which is pi minus inverse secant of x. So the thing about the inverse secant, ladies and gentlemen, is that there are two definitions that exist. When I teach calculus, I use this definition. So I teach this in my pre-cal class. And it is becoming pretty standard. And then, of course, on a lot of the literature and on Wikipedia, you get this definition. But it has some really nice attributes that you get a nice increasing function, you get the reciprocal rule, you get a lot of nice things. The only thing is that the derivative formula has an absolute value in it, which a lot of mathematicians don't seem to like. But I don't have a problem with it. Now, let's do the two more, and then we'll be done with these. The other two we don't spend a lot of time with, and it's not because they're unimportant. It's basically because I want everything to be consistent. I want you to be able to say that we've covered all of them. But when you take calculus, you spend most of the time on the first four that we've defined. Now, the next one will be the inverse cotangent. Again, what we're going to do is say y equals inverse cotangent of x if and only if x equals cotangent of y. And again, let me just write y equal arc cotangent. At least when we're doing x's, I don't have to use as many parentheses here, but that's another form of it. And like the inverse tangent, the domain will be all reals, but the range will live between 0 and pi. Open. And again, we don't get the in this particular case, when we think about this, we'll draw it and we'll see what is actually going on. I think what you'll notice here in this particular case is that even though it's not an odd function, it does still have some similar properties of the inverse tangent. So let's go ahead and write down the inverse rules. So in this case, cotangent of inverse cotangent of x will be x if and only if x is a real number, just like we've done many times before. I do these in the same order, so you'll see that all of this works the same. And then, of course, inverse cotangent of x, these absorb and give us x, as long as we end up in the range of the inverse cotangent, which is here, 0 to pi. So now we can draw it. So we'll have our pi over 2. That always gives us the 0. And then the pi. So these give us the horizontals. Remember, these are vertical in the parent function for cotangent. So we have y equals pi. And then we have y equals 0. So we get something like this. So this is y equals inverse cotangent of x. So it looks very similar to the inverse tangent, but it's certainly not odd, but it's easy to remember. Now, in this particular case, let me go ahead and write this down. We have, let's see, what do I want to write here? Yes, inverse cotangent of the negative argument. This looks like the one for the cosine and the secant. And this gives us pi minus inverse cotangent of x. And let me check to see on the secant if I gave you that. Yeah, similar, just like we have here for this one. These are all the same with the negatives if they're not odd. Don't spend a lot of time with this one, but I want to define it. And then the very last one is going to be the inverse secant. Excuse me, inverse cosecant. Lots of bookkeeping today. Inverse cosecant. So again, we're going to say y equals inverse cosecant if and only if x equals cosecant of y. And then again, of course, we have y equals arc cosecant of x is the alternative symbolism. Now, in this case, domain will look like it did for the inverse secant, which will be negative infinity to -1, union 1 to infinity. And then the range, it's going to look very much like the inverse secant, but things are going to be shifted down. So this is going to actually be an odd function. It will be negative pi over 2 to 0, open, union 0 to pi over 2. So this is a standard definition. And so now, number one, cosecant of inverse cosecant, and put the C there, will be x. They absorb if and only if x lives here. Needs to be in the range of the cosecant function. And then 2, inverse cosecant of cosecant of x will be x if and only if we are in the range. X is in the range, negative pi over 2 to 0, union 0 to pi over 2. So this is a really, really nice function. Let's draw it. Now, when you look at this, again, we've got our -1, or 1 and our -1. So we'll put this here, and then the -1. And we got this nice asymptote here, y equals 0. Now, when you think about this, we think of cosecant of pi over 2 is 1. So when we do inverse cosecant of 1, we get pi over 2. So we can do the same song and dance here. And I'll do this in the red. And then we descend to the asymptote. Do the same over here, negative pi over 2. So we descend away from the asymptote to the point. Right there. So we get a nice odd function, even though that's not a proof, it certainly appears that we have origin symmetry. So again, you know, we don't spend a lot of time with these functions basically because their calculus derivatives or their derivatives differ by negative signs. So it doesn't mean they're not important. It's just they don't get a whole lot of show in the calculus sequence, but I still want you to know them. And so we have a cosecant, inverse cosecant of the negative argument, it factors. So if you learn these graphs, you certainly can remember a lot of the attributes of these particular functions. So what's important here when you think about all of these is to put every one of these on note cards and to practice drawing them and working with them. Now, I want to do a couple of calculations, but there are some more complementary angle identities that I want to share with you that'll be useful in calculus 2. That is the complementary angles, so to speak. We'll say more about that when we do the cofunctions. That is inverse sine of x plus inverse cosine of x, of course, appropriately defined between -1 and 1. This equals pi over 2. These are the neatest formulas, identities in the world. Inverse tangent of x, and we may go over two of the proofs of these when we have time. This is pi over 2. These are complementary angles. Inverse secant plus inverse cosecant of x is pi over 2. Pi over 2 are 90 degrees, but we'll get to the angle measure, degree measure tomorrow or the next lecture. So I want you to be aware of these, and that's all I want you to have to kind of ingest right now. But these are really useful when you get to calculus, because now you can see here when you learn calculus, you can see why these derivatives differ by negative signs. These identities give you some nice calculus. So when you get to Cal 2, it's always nice to have these in your back pocket so you can, use them. That's where this will get the most use in your calculus sequence, or most use when you get to calculus. Right now, we're just learning about them, and you might be thinking, well, not so interesting, but it'll be interesting later. Now I've got a few examples here that I want to just kind of, now that we have these inverse trig functions on the table, let's just do some simple calculations. So for instance, if we just want to think about working the inverse or the unit circle backwards. So let's look at a simple example. Well, what's the inverse tangent of 1? Well, let's not even guess at it. Let's go back here. Let me get to my picture. Too many pictures. We have this, right? So we're going to say that this equals y. Now, what does this mean? If and only if what? 1 equals tangent y. Well, what input on the unit circle gives us this that actually lives between negative pi over 2 and pi over 2, pi over 4? So we'll say if and only if y equals pi over 4. Now, what's important here is that this must lie in the actual range. So remember, the inverse tangent of x lives between pi over 2 and negative pi over 2. So whatever answer I have here must live in this interval. That's why you need to know the definitions of the inverse trig functions, because again, when we put an answer here, there are plenty of values that we could substitute here. We could use 3 pi over 4. That tangent of 3 pi over 4 is 1, but it's not in the inverse trig range. You see, there's only going to be one value because the function is 1 to 1. Okay, so when we think about evaluating inverse trig functions with the points on the unit circle, we just go from the terminal point to the t value. So we work the unit circle backwards. So here's another one. Say we have inverse cosine, let's say -1/√2. Okay, now let's just think, this is y, if and only if -1/√2 equals cosine y. Now, what we want to do is make sure that we have a value that lives in the range of the inverse cosine. But remember, inverse cosine of x lives between pi and 0. So in this case, we would have to go into the second quadrant, and this would be what? 3 pi over 4. So if and only if y equals 3 pi over 4. So clearly it's not pi over 4 because this is negative, and you can't say negative pi over 4 because that's not in this interval. So we have to, again, go back to our definition of the inverse cosine. So again, these are simple. This is, most students say, oh, I get it. It's just the unit circle. And in Cal 2, oh, well, Professor Ron, I just use the unit circle. I'll say that's fine, but think about what you're doing so you don't make careless mistakes, okay? So what we're seeing here is that when it comes to the standard terminal points and t values on the unit circle, we don't have anything new to do. We just, instead of taking the forward path, we do the reverse path. Okay, let's try another one. Let's say we do a inverse sine or something. So we do inverse sine of -√3/2. Now let's do this a little bit different at first. So now we're going to say, okay, well, we know that the inverse sine function, well, we didn't use the identity here. We just, did it by virtue of the fact of the definition. But if we did this one, we're thinking, well, we know the inverse sine function is odd. So we can say this equals the negative of inverse sine of √3/2. And now we'll just do this in a forward direction. And we know that the inverse sine of x, I'll write it this way, I'll just use the set notation, lives between -pi/2 and pi/2. So this part here will be in the first quadrant, and that's going to be what? Pi/3, and then made negative. So this will be -pi/3. Indeed, the sine of -pi/3 is -√3/2. So again, we're playing this game of going forwards and backwards, but we're also adhering to the actual ranges of the inverse trig functions. That's the only catch, okay? So when you do this, this is why it's good to have the picture of the inverse sine function in your head, thinking, oh, okay, well, this output has to live between -pi/2 and pi/2. So if I go beyond that, then it's going to be what we call undefined, okay, undefined. So you don't want to give something that's not defined. I mean, and again, this is very symbolic because it rests upon the definitions of the inverse trig functions. Okay, let's try some more. These are kind of fun. This is like being on the quiz show. Wouldn't it be neat if they had a math category on the quiz show? You all could go to Jeopardy and make plenty of money, but I don't think they're ever going to have a math category. They never seem to. I think that we miss out that way. Now let's try some of these inverse equations. Say we do, let's see, inverse cosine of cosine of, let's say, 2 pi/3. Okay, so that's one of the inverse rules. Now I'm going to write this down just to remind you. This is what I wrote down before. This equals x if and only if x lives here, right? This is the rule based on how we've defined these things, okay? So now when we look at this, we're thinking, oh, I can just write x as long as the x lives here in this interval, and it does. 2 pi/3 is in this interval between 0 and pi, so we say 2 pi/3, okay? So the key here, again, let me find the sheet. I think it's covered up. It's amazing when I go back and look at all of the notes I generate, I get a pile by the end of the term that's like this. And then I told one student, I just throw them all away and start over. Kind of crazy, right? When I look here, remember when we define this, if you look at this, you see the range is here. This is how we define the inverse sine function. And then we go to here, right? So when we look at this particular problem, this is just a statement of what we defined about the inverse cosine. So here I repeated it. So this would just be the x, because again, it satisfies this. You see? So you're thinking if we do this one will always be really easy because it's either going to be defined or it's not. The flexibility exists here because of the cosine function, but these are never a problem. If they're not defined, you don't do them. You're just like, I'm done with this. But the number two here always introduces more complexity. So let's just look at this. So let's look at this example here. We'll take the same function so you can see how we may have to make an adjustment. So we have cosine, inverse cosine. Say we have cosine of, let's look at it this way. Let's say we do 5 pi over 3. Okay? So now you look at that and say, okay, well, we know in this case, if we do this, we've got this rule here. That's too big. That's not in this interval. So first we say, okay, what's 5 pi over 3? So we got 3 pi over 3, and then we have 4 pi over 3. This is in the what? Fourth quadrant, right? So let's go ahead and look at this in terms of reference number. So if we call this, let's just call that x, then x bar will be 2 pi minus 5 pi over 3, which is 6 pi over 3. So that's pi over 3, right? Okay. So now we can say, and this of course is in the fourth quadrant, the cosine is positive there. So we can now say this equals inverse cosine of pi over 3. These are equal. So we just do a little sidebar calculation with reference number, okay? And so we see if we're taking the cosine of 5 pi over 3, that's equivalent to the cosine of pi over 3. So we can make this exchange here. But now pi over 3 lives here. And then we say pi over 3. So this is where you have to be very careful. Again, if this does not live in the required interval, then we have to make a suitable change, an equivalency. And then we'll say, oh, that equals this because this now satisfies the definition of the inverse what? Cosine. So that's why I defined all of these functions. And what you need to do now is you need to put all these on note cards and learn them, okay? You can't, this is kind of like trying to graph a cosine function and you don't know the principal points, you see? So with all the inverse trig functions, these need to go on note cards and you need to learn these because as you do these types of problems, you have to use the fact that you know the required range of the inverse cosine, and that directs you as to how you solve this problem, okay? So students are like, well, I can use a fancy calculator. Well, no, you can't. I mean, I guess you can in another class. But here's the deal, folks. Understanding mathematics means that you can actually do the computations. We go to Google to get a nice calculus approximation after we've done all the work, and we need a nice approximation to make the web assign happy or to make the test happy. Or Professor Ron could just say, here's the exact answer, give me the exact kind of thing. So what we want to focus on is the process using our definitions of the inverse trig functions and using that knowledge to be able to make these types of computations. Now, of course, the computer algebra systems and things have all these rules encoded in them through their coding. And so that's why they can give you nice results. But what I found many times is many science students start to take information from a calculator that's inconsistent, or they're getting undefined or error or whatever because they're not applying the mathematics correctly. So what we'll do on the next class, we'll do a few more examples of this, and then we'll talk about degree measure and arc length and sector area and all kinds of fun things like that. Then you're going to think you're in a physics class. So the next lecture, you're going to think, oh, this is the fun trigonometry. Why didn't we start with this? So we'll do some of that on the next lecture to kind of bring you away from the unit circle into the degree measure as we forge into the right triangles that are superimposed on the unit circle. So we will now be shifting to the second interpretation of trigonometry and then basically see how they come together. But with the triangles, we will have a new way of classifying certain problems. So we start with the unit circle to get the graphs, to get the inverse trig functions, and then we look at the triangles to solve nice problems in physics and mathematics that are very important to us. So if you know some of the students at San Jac that are doing some of the certifications, like in plumbing and electrician and things like that, very technical programs, they use trigonometry, but they focus on the right triangle trigonometry because that's what they need for their disciplines. They don't really need the unit circle, and they're going to focus more on degree measure. But again, that's fine. Whatever discipline you need is what you have to study. And of course, since you're going to be STEM majors, you need both. So you don't get to choose. Okay. Well, it was again, I'm sorry about the less climatable, that's not even a word, the less nice weather. We have to put up with some rain now because we had Palm Springs weather last week. I mean, let's face it, we were so blessed last week. This week, if we have some rain, we will survive. So I appreciate your attendance today. Get your trig functions, inverse trig functions in your brain. Get all these parent functions in your brain. Get them on note cards. Put them up here. We will need them, and we will use them often. And of course, when you get to calculus, you know, if you don't learn it now, it's just going to go to dust by the time you need it. So get busy getting these in your brain, and we will see you at the next class, if not at office hours. Everybody have a great day.